now the presentation of Jason Trout from SADRAM, and after that, Patricia Gonzalez Guerrero from LBL. And after that, we will have a conference photo, and I keep talking, waiting for someone else to come in, but we are who we are. So, Jason, please go ahead. Thank you very much.
All right, greetings all. My name is Jason Trout. I'm here to talk about the new processing near memory architecture that we're developing. It's called SADRAM. All right, so you'll remember Robert, my father, was eulogized at the start of the events here. We lost him in November to cancer, so I miss the man and I miss his help. Rest in peace, you damn rascal. So now I lead our team. I'm based in Tucson, Arizona. I'm assisted by my stepson, Spencer. Nicholas serves as our CCO, and Will Camp I consult with on technical matters. We're probably going to wind up here in New Zealand in about a year's time. Hey, Gail. So if I pique your interest with any of this, I hope you'll come talk to one of us, because we need help. We need an industry partner to make SADRAM real, and we need guidance, because I certainly don't have all the answers. All right, so what is SADRAM? Zoomed all the way out, SADRAM is an augmented a processing near memory architecture, which augments DRAM by putting an autonomous database next to DRAM chips and within DRAM chips. Now, you can add record data associated with a key. You can delete data, and you can read data in the quote-unquote sorted order. Let's see if I forgot. Nope. Okay. So why is that interesting? First, it's near memory. It's either going to be a PCIe coprocessor or it's going to be upgraded DRAM, but either way, it's close to the storage of data. So we're expecting power savings and speed improvements from being close to data. Second, it's autonomous. It's a coprocessor. It's your CPU can go off and do other things once it gets SADRAM started. And it implements a database. Databases are everywhere today. You use databases every time you're doing a mobile app, every time you're doing an app online, every time you're recording complex sensor data. These slides are a simple database. So if we can make a material improvement in how databases are organized or how databases are computed, then there'll be an outsized impact. So what we're working on right now, Robert left us with a proof of concept that's implemented on a Crea KV260, which is a relatively small starter FPGA. We're currently moving to an Alveo V80, which is an FPGA something like 20 times the LUTs. But more importantly, it's got access to high bandwidth memory. We're using high bandwidth memory to simulate access to the DRAM row buffer, direct access. And that's, the Alveo's got enough storage on its onboard HBM to store, a sizable database. I think I did the math at 252 mega keys. So a reasonable database. And certainly not multi-system, but reasonable, enough to take some benchmarks. I pull up benchmarks because we still need to develop them. The plan is to make a modified SQLite implementation that takes advantage of SADRAM, and then we can produce power and speed benchmarks based off of that, and then present that next year. So watch this space. Yeah. All right. Does anybody need a refresher on how B-trees works? Or sorry, on how binary search trees work? Nobody. Okay, that's fine. So then we'll skip it. It's the sentence version is you start with a root node, you're traversing pointers all the way down until you find the data, and you traverse left or right based on if you need. You traverse left or right based on the data that you're looking for. And it runs at traversal complexity log of n. This is basic computer science. So B trees. How about B trees? Is everybody familiar with B trees, or should I go into detail there? All right. All right. So B-trees is different, is an improvement on binary search trees. And it's an elaboration. So the difference, if you look at this slide, every number's got one node. In this one, we pack multiple numbers into a single node. That allows for more subnodes here at the bottom. So 1, 2, 3, 4, 5 subnodes, which means that B-trees uses a higher fan out than regular binary search trees. Now that improves the speed at which you traverse the trees. This one you're going through this at log base 5 of n rather than log base 2 of n for any of these trees. But the comparison, a wider fan out means that there needs to be more comparisons within each node traversal. So 1, 2, 3, like these 4 results when compared with 3.2, all 4 of these results have to be combined in order to say, oh, I want to traverse to this node or this node or this node or this node, yada, yada, yada. So we interpret that as locating the edge in the comparison results. So the edge is where we stop getting less than results and when we start getting greater than or equal to results. So for 3.2, obviously the edge is between 2 and 5. And here's the edge line right there. And then on the left, same story, 3.2, between 2.5 and 3.7, edge is between them. Now I have 2 examples here because in an internal node or in a leaf node, the behavior of what you do is different. You're either going to insert the data in the case of a leaf node and make space for it by shifting any data that needs to be moved in order to keep the data within the node in sorted order. You shift that to the right, and then you insert the data in the hole that creates. That's for a leaf node. For an internal node, it's following a pointer. So this pointer leads down to this node, which is this right here. Now, this sort of graphic might confuse you of whether we're doing a binary search or a linear search when we're talking about the nodes, the values within a node. Of course, it'll be a binary search in the case of B-trees because it's faster for a single-threaded process. We tend to present it this way because SADRAM is designed to do all of its comparisons in one lick, right? So we have comparators that can do this comparison, all of these comparisons in constant time. All right, so my wife's contribution, I'm sure everybody has made the joke. We're unhappy sheep. All right, B-trees, like most current algorithms, is limited by the memory wall. Our research shows that B-trees fan-outs, how many nodes you get from level n to level n plus 1, is 10 to the 3 or 10 to the 4 when you're talking about disk-based systems, or 8 to 64 when you're talking about systems that are backed by DRAM. The fan-out sizes are selected in order to minimize trips to the hardware, obviously. You want to spend as much time as you can in the cache, or you want to get as much data, value for data as you can when you go out to disk and grab a whole page. So hardware trips are also reduced by minimizing the amount of data that is associated with the search, right? So in this previous example, the only data that we are storing inside the node are the numbers themselves. There can be data that's associated with these numbers. We refer to that as record data, and these are keys, 1, 2, 5, and 6 keys, and then if this was associated with a seating chart, these might be students where they were sitting. That might be the record data. So we don't store the record data. We don't store any of the student data that's not important for where they would be sorted. Those are associated with a record, and we store a pointer to that record. So B-trees and SADRAM are both working with key pointer pairs, and you'll see the key and the pointer when I get down into the hardware, into the example of doing an insert in hardware. Okay, the last wrinkle, keys are not required. in B trees, sometimes they're omitted if you're just sorting numbers, or they'll be blank, depending on how well your algorithm is optimized. All right, enough about stuff that isn't SADRAM. So, SADRAM is a processing near memory solution. It's augmenting DRAM, so it's adding extra functionality on top of DRAM. You write to SADRAM as you would just DRAM. You write record data to it. SADRAM is going to act as a man in the middle. It's going to trigger when it recognizes a key within a stream of record data. It's going to take a copy of that. It's going to take that copy and put it into and sort it and put it into a memory area of its that's dedicated for the purpose called an index space. That is the process of key insertion. Later on, you can do a read by key, which is you're presenting a key to SADRAM and you're recovering the pointer to that record. And then the key insertion and the read by key operations together are what gives us our name. They make us symbolically addressable. SADRAM, SADRAM. All right, so components. We have, the first thing that we're going to spend a lot of time with here is the sequencer. So that is in light blue there. This is custom logic that's added to a DRAM buffer. This is capable, we saw earlier, it's capable of doing shift logic, so making room for data within the row buffer of DRAM. And it's also capable of doing comparisons, simultaneous comparisons, or if we have to make compromises, a binary search kind of comparison as well, logic compromises. Second is the SAMPU, that's here in blue. So that's a general purpose processor, performs maintenance operations on the index space. Basically anything that it's too expensive to do in logic gets handled by the SAMPU. And third is record memory. This is most of the chip, and it's just DRAM. So if we're assuming that most of the data associated with a record is not key data, is not stuff that you typically need to sort on. So that's where this is going. It's all in this enormous block of standard DRAM storage. That's the last probably I'm going to say about record RAM. All right, so originally we conceived of SADRAM as existing in DRAM slots. We want to take advantage of the fastest available connection. We're probably, for our first prototype, we're talking about being in a PCIe slot hooked up with a CXL protocol. CXL protocol gives us a data link, and it also gives us a configuration link, because we need to be able to define where the key is within the record. We also need to be able to find where what kind of data it is, right? Because SADRAM only really sorts data lexicographically, right? So A before B, B before C, etc. Okay. All right. So we got a simplified DRAM picture here. We're going to look at the sequencer. This is the novel logic. I'm going to spend a little bit of time down here. So we got a simplified DRAM schematic here. We got the cell array up here. This is a bunch of transistor capacitor pairs. So each one of these intersections is a 1T, 1C cell. So one transistor, one capacitor. Down here, we got a bunch of sense amps. The sense amps' job is to boost the tiny voltages that are stored up here in the 1T, 1C cells up into rail voltage, stuff that we can actually do logic with. Together, all of this is referred to as the row buffer. I used that term before. So it's just a bunch of sense amps ganged together. All right, and then for the rest of this, we have some bus out to the rest of the world, some control logic, and a row decoder over here. All right, so when you're using DRAM, you open a row. So you're going to latch a row down here, and that's going to pick one of these rows that we got. We latched 3, and that's going to decode into row 0, 1, 2, 3, and then the 1T1Cs that are here are going to release their charge, which flow down these vertical lines, those are called the bit lines, down into the sense amps. So, and there they stay while the row is open. Yes. There they stay while the row is open. While the row is open, you may be familiar with the term cache hits or cache misses. This is what they're talking about. While this row is open, we can do reads and writes on this data right here, and it doesn't cost us power and it doesn't cost us time. So if we're doing a read, we're going to select one of the columns or a subset of the columns, depending on how wide this bus is. In this case, I'm selecting column 1, which means we're going to grab this guy and drive that data EF out here, out to the bus, where it joins, I don't know, 16, 32, or 31 other chips like this in order to create the DRAM bus. If we're going to do a write, then we're taking data that's coming in from the DRAM bus, and we're modifying this data somewhere in this row. When that's all done, when you're done with the data that's in this row, you're going to close the row because you need the 1T1Cs for something else, for one of these other rows that isn't currently selected. So then this data goes back up into the row that it came from, and then you open another row. All right, so why is that's not SADRAM? This is SADRAM. SADRAM is performing sorting operations on the row while it's open. When commanded by the SAMPU, which is that blue box that I was showing earlier, the general purpose processor, the sequencer is comparing keys on the data lines against all of the keys that are in the row buffer, right? So we're storing key pointer pairs within each one of these row buffers. And what the sequencer can do is take data on this bus and compare them on the row data that is open. So, like B trees, SADRAM's employing a tree structure in order to get traversal time for the tree selecting data that you're looking for down to logarithmic time. Like B trees, it's a larger base logarithm than just base 2. It's based on the fan out that your row/node has. So for us, we're expecting, given a typical row size and a typical key and pointer size of 64 to 128, pairs favorably against DRAM-backed B-trees implementations. So I already said this. It works with keys, stores multiple keys within a node. You've got to pull one of these rows/nodes down into the sequencer before you can do any work. Like B trees, SADRAM keeps the data within the row in sorted order. So currently our design is doing the comparisons that would be necessary to keep them in sorted order simultaneously. We may not be able to do that if we have to make compromises for how much logic we can put down here. I mean, this is on the DRAM die, so it ain't cheap to put complex logic on this. So if we can't have a simultaneous comparison, then we go with the binary search tree pattern. Or we search through this with a binary chop. All right. So, like B trees, we're maximizing the value for each hardware read that we do. For us, the hardware read that we're trying to minimize is how many rows we open. So this row, like it says up here, is likely to be 8192. That's a pretty good industry standard. 16384 variants do exist. So if we're based off one of those, that's another 2x on our fan out. And I already said this, manipulates key pointer pairs. All right, so we'll go through inserting data. Into the sequencer now. So pictured here, we got four things called a cell group. All right, so that's 1, 2, 3, 4. So each one of these cell groups is made up of sequencer cells. That's these guys here with the red numbers in, and also the orange numbers in. Those are all sequencer cells. Now, those are triangles. If you've been paying attention, the triangles are what I used previously for the sense amps, right? So these are the sense amps that we inherit from traditional DRAMs. So these are pictured as being able to store 8 bits. Obviously, that's not true because they're 1T, 1C cells. These are, in actuality, 1-bit cells. They're pictured here as 8 so that we can track numbers as I walk you guys through the example. Now, the other thing to note, we're broken into 2 groups. Obviously, the row buffer exists on 1 line. So this is 2 chunks of 1 line, and there's going to be 128 or 64 of these cell groups that are on the row buffer. All right, now the key pointer pair that we're presenting is right here. It's in teal. The teal section is the value, is the key that we're presenting, and this pink value is the pointer that we're presenting. This is zeroed because I'm trying to keep this example as simple as possible, so there are no associated records with this. We're just working with that number there. The new key, okay, and then we're distributing that to each one of these black boxes here, and that's supposed to represent being compared to this data that's already in the cells. All right, so we're showing here 16 bits for key and for pointer, so red and orange, that's key and pointer, 16 bits. SADRAM can support variable key sizes in hardware. We typically consider 64 bits to be typical. Last year Robert showed this as sorting string data. I tend to prefer to think of this as integer data. It doesn't matter that much. I mean, it's just a question of do you need to rearrange integer data into a lexicographic format before you start. All right, so I said before, these red and orange values are the key and pointer data in the sense amps, the cell values. So this is the pointer here, and that is a reference to a row in SADRAM, right? So this is an internal node, because we're in the process of traversing from the middle of the tree down to one of the leaf nodes, this is an internal node, and these pointers are referring to other SADRAM rows. So here in cell group 2, that 07, that's a reference to row 7, whereas we are currently on row 4, and I just made that up. All right, the keys, this one here, or this one here, because this is an internal node, these represent ranges of keys that are more exactly represented in the subnodes of this node. So this is a bit of a mouthful. The key in each cell group is maintained as the minimum key in that cell group's subnode, and the key in the subsequent cell group is strictly greater than any key in the previous cell group subnode. So I cannot get through that without reading it off my script. But what it means is that because this is referencing row 6, this pointer is referencing row 6, this key is 1201, and this key in cell group 2 is 1220. Therefore, all the values that are on row 6 are between 1201 and 1220. All right. Now, the other thing that we can do within the sequencer is compare numbers. That's what's going on here, or that's what I'm trying to represent here and here and here and here and down here and down here. So, comparison is bitwise in SADRAM, and a carry bit propagates through the cell group. So what we're doing, again, we're comparing 1201 here to 1234 here, and again, 1220 here, 1234 there, et cetera, et cetera. All right, so all bits in the 2 keys are compared simultaneously, and if the 2 bits are equal, then a carry bit propagates through each cell in the cell group until you get a result that is non-equal. So what we can see here is that this comparison and this comparison, so the first 8 bits of these comparisons were inconclusive because 12 equals 12 here, here, and also down here. We only get the answer once we get down here. All right. Now, pointers don't participate in the comparison, just like in B-trees. And what also doesn't participate is any data that does not have doesn't have a key pointer in it. In this case, cell group 4 doesn't have anything in it. That's what these null set values are supposed to represent. All right. Now, like I was saying before, talking about locating the edge in the comparison results. The edge for SADRAM is the last false result that you're getting in the series of greater than or less than results. So the edge in this case is right here in cell group 2 because 1220 is less than 1234, but 1240 is greater than 1234. So, and we're going to traverse because this is an internal, which means that we're going to traverse to this row right here, row 7. I'll stop talking about internal nodes now. There are a couple differences when you're talking about a leaf node. The pointers point to records when you're talking about leaf nodes. So if you'll remember all our record data in here. So when you're talking about leaf nodes, this pointers to this stuff. Yep. And then the keys are no longer representing ranges of values; they are just themselves, right? So at some point at some point there really is a 1201 value or a 1220 value. All right. So traversing to a different node means we have to close the row. So this is all the free computation we can get on this row is just traversing a node. We have to open the next row in order to continue. So we're going to open row 7. That's not what I wanted. We're going to open row 7, and here's row 7. We're going to do a comparison that's similar to the comparison that we just did, and we're going to find the edge, and then we're going to insert the new data into this row. The data, if you'll recall, is still in teal and pink. And we've had to shift the data we had to shift data in order to make room for it. So like the previous cell, this had 3 entries in it, 1220, 1235, 1239, and then the last one was null. And now we have to have 1234 so that we're filling up all of the space in this row that I'm showing you guys. With this, all the keys are still kept within sorted order within the node. Now the shift that I've shown here is not overwriting any data because there was space here, like this node was empty. SADRAM has to be kept in that state perpetually, such that there's space to accept a new key pointer pair when it is presented. So SADRAM guarantees that by performing row splitting on these rows. Now, I designed this talk not to go into that because I didn't think I'd have time. We can go over that during question time if there is any. All right. All right, so the other operations that a sequencer can do, you can read by a key. So that's that's the read operation analog to what I just showed, which was inserting a key. The differences are you're going to present a key only to SADRAM. You don't present a key pointer pair. Obviously, you don't have the pointer. The point is to be able to find the record only having been given the key. Second, leaf comparison looks only for an equal value. So you're not looking for the edge is no longer defined as the first place where less than values switch over to greater than values. The edge is defined on leaf nodes as the first equal value. And you can also find that the data is not in the database at all, in which case there is no edge, in which case 0 is returned. Now, if it does find an edge, it will return the pointer, and then you recover the pointer just like a standard pointer access. Now, the second thing is read by index. Read by index is, this is another one where I didn't go into the details for time, but read by index is basically achieving the same thing as if this were data laid down in a sorted array like you would have sorted in C. So that's kind of complicated how that's achieved given that our data is sort of scattered through this tree series, but it works. And then the last one is key deletion. So key deletion, we typically mark the data as invalid rather than remove it from the database because there's sort of upstream effects that can happen if you're deleting data deleting data out of the leaf nodes, if that has an effect on nodes that are higher up in the tree. So we mark the data as invalid, but only remove the data from the tree when SADRAM is idle. All right, so I think I've spent most of my time talking about the sequencer because it's the piece of novel logic. It needs a partner to handle things that are too expensive to do on the DRAM die. Row splitting being one. Watching the DRAM bus for data as it's being presented is two. And cleaning up after deletes is the third. And there may be other tasks that we haven't fully cooked up yet. Tasks like these are handled by the SAMPU. As the name suggests, this is a general purpose processor with some customizations that make it possible to trigger sequencer operations. Robert Trout invented this. It's patented for SADRAM Incorporated. It operates as a coprocessor, as I said previously. It's completely independent of the CPU. A single core, very lightweight, runs at 100 megahertz, on 1.25 megabytes total program memory, 16-bit instruction set, 8 registers, 16 global, small, very small. Does have debug controls, and in order to use that, we currently have a suite of software that allows you to compile programs that are written in a language that Robert invented called SAM code. You can boil that down into assembler instructions for the SAMPU. Now that set of instructions is including basic math, doesn't have multiply and divide, but add, subtract, and all the bitwise stuff. It supports functions, loops, conditionals, and the specific sequencer instructions that I was talking about earlier. So think what we are considering now is a move to RISC-V. Dad tended to invent all his own tools. So RISC-V is obviously more accessible to the outside world. And we don't have to reinvent the wheel. I mean, Dad spent 2 years writing all the various software components in order to support the SAMPU. On the other hand, we're going to have to reinvent some wheels because we've got to reinvent the sequencer-specific instructions if they're going to go on RISC-V. I think that's the smaller lift. So that's what we're probably going to do. All right. Now, what can you do with SADRAM? Why do we care? Why should you care? SADRAM is going to be damn good at database applications. Reading and writing by key is sort of the bread and butter of doing database accesses, and that's what we're optimized for. Databases, as I said, are everywhere. So outsized impact, as I said. We should be very good at sorting as well, just sorting basic numbers. The read by index command that I was talking about earlier allows you to read pointers in the quote unquote sorted order, as though it were an array a C array that had been sorted. So SADRAM, and the interesting detail here is SADRAM sorts data as it stores it. So if you have data that is getting freshly generated by a sensor or something, and you're wanting to have its first port of call being SADRAM, you get the sort for free. All right, so everybody's talking about AI recently, of course. So SADRAM can increase effective memory density, and that has an effect on hash tables and on AI. My experience with hashing tables is that they're not perfect. You have collisions, or you're going to wind up scattering the data into various locations in RAM with a lot of space between them. So you're eating up extra memory when you do that. And it's the same story when you're talking about sparsely populated arrays. There's a lot of sparsely populated arrays that AI is using for nodes that aren't carrying any useful data, right? So if there's a part of the connectome that isn't indicative of anything useful, then that will be represented by a weight of 0. And also, any training data, if that any trading data that you want to back propagate against that connectome winds up can go to 0 if there's not going to be any change on those node weights. So the concept of SADRAM is you're not accessing any of those node weights by its location. You're accessing it by a key. So that means that if those node weights are 0 or those modifications to node weights are 0, you don't have to store them. You just have to store the stuff that's relevant. You just have to store the stuff that is not obvious. All right, finally, SAMPU is expected to be on the far side of the memory wall. So the point is this is a processor. It's coupled very closely to your DRAM storage. This might be a similar situation to caches, right? So when caches were first introduced, we had an enormous speed up, 5 to 50-fold, for any algorithm that could fit most of its needs in the cache. We have, SADRAM being right next to memory has similar access, but to a much wider area of memory. Now the processor is weaker, but if you are memory constrained rather than compute constrained, that's maybe a trade-off you can accept. All right, so what are we working on? As I mentioned, we have a sort of a toy example that's implemented on a Crea KV260. I don't know if anybody knows, and if anybody here knows what kind of FPGA it is. I mean, I think it's for students. You can buy it for like $260. So we have an implementation of SADRAM done on that Crea KV260. It's a functional model. It's too small to do anything really beefy with it. What I'm working on right now is to take that model and move it to the Alveo V80. So Alveo V80's got 20 times the LUTs and access to high bandwidth memory. High bandwidth memory, in this case, what we're going to do with it is sort of gang them all together into an 8192 wide or 16384 wide bus in order to simulate those row buffer, in order to simulate the row buffer that I was showing you earlier. Right? There's no other way to get a bus that wide without a lot of independent memory, and that's what HBM gives us. So 8192 or 16384 happy coincidence. That's the widths that we're trying to hit when you're talking about standard DRAM chips. So the only downside here is that you have to, in order to join all those buses together, because it's provided to the fabric as 64 256-bit AXI buses. So you got to sort of take all those buses and combine them together, and it takes a little bit more latency. So it's close, but not a slam dunk for a real row buffer in real SADRAM hardware. Beyond that, we need to, we're eyeing improvements to the SAMPU and the sequencer. So I didn't mention SRAM in any of this. So obviously, when you're talking about the root node, access to the root node, that can be in a piece of memory. That is faster than DRAM. So obviously, you keep that in an SRAM cache. You're going to probably also segregate keys and pointers onto their own rows, which is going to give us a fan out of 2x. What that means on the downside is we have to open 2 rows. But we can stagger their opening because you need the pointers in order to decide where to go, and you don't need the point. You can stagger the keys, and you need the keys first, right? You need to do the comparison first, and then you do the row traversal. So you don't need the key data, and you can delay that row's open until after you've decided where to go, or preferably pipeline it so that the key row is sort of buffered in a local cache, and then you can go out and open the pointer row. And then, yes, the RISC-V. And it's a big lift to move to the RISC-V, and so probably our initial examples, when we have a working prototype, is going to retain the SAMPU and SAM code. All right, so I'm seeing plenty of things that make me interested about SADRAM, but we don't have all the answers. I don't know how to implement, I don't know how to create this stuff, right? We obviously need a chip, because what are we targeting? We're trying to target DRAM we're trying to target a price point that's DRAM but with extra features. I mean, the goal would be to get SADRAM in a lot of different kind of systems, and only the people that need it are going to turn on the SADRAM-like features. Now, these are sort of the questions that I wanted to put up to the group. If you guys had any input on this, come and see us because we need the help. And I don't need to read through all this. If you guys want to have a conversation, we'll just leave it at that. We're sort of running low. So I'm going to leave you with this, and then I'm going to leave this slide up while we have question time. And again, SADRAM, dumb visual jokes. So we're augmented DRAM. We're trying to do databases in local hardware. So we're trying to be a hardware accelerator. Databases are common, and if we can do better than what we're doing now as an industry, then we should have an outsized impact. And yeah, we need your help. We need to figure out how we're going to build this stuff.